Okay, we're all set. Hi everybody. Welcome to a new episode of our machine learning security seminars. Today we have Alina Oprea from the Northeastern University of Boston with a talk titled "On the Way Forward Towards Trustworthy AI Agents." So, for your information, this presentation will be recorded. So, we kindly ask you to accept the privacy policy when joining the seminar. Also, we will upload the recording to our YouTube channel, where you can find all the information about the seminar and all the recordings from past events. If you're interested in learning more about these topics, you'll find a short course on machine learning security on the same YouTube channel. Before we start, I want to thank also the other co-organizers of this seminar series. Among them is Maura, who will introduce today's speaker.
Hello, thank you, Giorgio. So I'm very happy today to introduce Alina Oprea. She's a professor at Northeastern University in the Khoury College of Computer Science, where she co-directs the Network and Distributed System Security Lab. She joined the Northeastern University in fall 2016 after spending 9 years as a research scientist at RSA Laboratories. She received several awards: the Technology Review TR35 Award for Research in Cloud Security in 2011, the Google Security and Privacy Award in 2019, the Ruth and Joel Spira Award for Excellence in Teaching in 2020, and the CMU Cylab Distinguished Alumni Award in 2024. Her research interests are trustworthy AI, security of agentic AI systems, AI for cybersecurity, machine learning privacy, and cloud security. She is currently general chair of the IEEE Symposium on Security and Privacy 2026. And now we are ready to start. So Alina, feel free to start when you're ready.
Okay, thank you very much. Can you hear me well? Yeah, thank you very much for the nice introduction, Maura, and thank you for inviting me to today's seminar. It's a pleasure to be here, and today I want to talk about a bit of history in adversarial machine learning and how can we make AI systems more trustworthy. In the last few years, we have seen a lot of progress on AI, being used in a number of different applications and domains, like language technologies, in science, in healthcare, and software. But what can go wrong? So there are a number of documented security and privacy risks against AI systems, for example, including leakage of sensitive confidential user data, or using AI for launching a cyber espionage campaign. Also, indirect prompt injection attacks that can hijack a model or an agent's execution and can lead to, adversarial objectives. And so adversarial machine learning is the research area at the intersection of AI and cybersecurity, and its goals are to study the vulnerabilities of AI algorithms in face of adversarial attacks. And of course, the end goal is not just to study the attacks, but the end goal is to develop mitigations and understand what are the challenges and what are the limitations in this space. And this is not new, as many of you know. The first attacks were developed more than 20 years ago, in 2004. But I think in the last 10 years, this area has gained a lot of traction. And the turning point, I think, in this space, in adversarial machine learning, was the discovery of adversarial examples in deep neural networks. So several concurrent works in 2013, 2014, they found that neural networks are not resilient to small adversarial manipulation. In particular, if an adversary can perturb a test sample, it can induce misclassification in the model's prediction. And these attacks were originally discovered for computer vision applications, but of course, they are applicable in other settings like NLP, healthcare, or connected cars. And so this is a timeline of research in adversarial ML that I kind of tried to put together in a simplified way. Of course, there are more events that have happened over the years, but Initially, since 2004, I would say for about 10 years until 2014, the attacks were developed for small-scale models. And during that time, I think a lot of work was done on defining threat models, coming up with a terminology of attacks in this space. But since 2014, with the discovery of adversarial examples, I think after that, for about 8 years or so, a lot of focus has been on studying the risks, adversarial risk in neural networks used for classification or regression. So this is predictive AI. And then since 2022, when ChatGPT was released in November of that year, the community has shifted on studying the risks in generative AI systems. And more recently, in the last year or so, we see a lot of agentic AI applications. And of course, there are many security and privacy risks in this space as well. So together with NIST is the National Institute of Standard and Technology in the United States. And we collaborated in the last 3-4 years on trying to put together a taxonomy of attacks and mitigations in adversarial machine learning. We had the first report released in 2023, and since then we try to update it every year because there is a lot of, there are a lot of new attacks, a lot of new mitigations, a lot is happening in this space. So if you look at the report from 2023, it already feels outdated. And so every year we try to update it, and we're already working on the 2026 edition, where we will add a new section on agentic AI risk. Like 2025, we didn't have the agentic AI, so that's a new chapter that we're currently working on. And so every year we release this report. Initially, we release it as a draft, and so we welcome comments and recommendations from the community. In particular, are there any latest attacks or mitigations or any trends that we are missing? And there is a period for comments, right, for about a month or so, and then we take that feedback into account before publishing the final report. So I think somewhere at the end of the summer, hopefully we will have the 2026 edition, and we are always looking for feedback. So please get in touch if you'd like to contribute. So with this introduction, the agenda for today is that I will discuss about how adversarial ML has evolved historically from predictive AI risk. I will talk very little about that. Then I will focus on generative AI risks, and then second half of the talk on agentic AI risks. And throughout this, I will talk about different attacks we have developed and different mitigations to make AI systems more trustworthy. That's the end goal. And so in the predictive AI world, this is a lot of research has been done in this period, 2014 to 2022. The setting is quite simple. In these predictive models, we have a training phase where the model is trained on some labeled data, and then we have an inference or deployment phase. And there are 3 types of attacks. The first one is poisoning attacks. So these are attacks at training time, where the attacker controls either a subset of the training data or the model parameters. And then at inference time, we have evasion attacks. These are adversarial examples where the attacker can manipulate the testing sample, and privacy attacks where the attacker can query the trained model in order to learn information about the training data or the model parameters. So these are the 3 main classes of attacks: poisoning, evasion, privacy. But most of the literature, I think, during this period was written on adversarial examples, on evasion attacks. We have thousands and thousands of papers with different threat models, ranging from white box to black box, different kinds of optimization, different procedures of coming up with the best, adversarial examples. So what did we learn after all this work has been done? So I want to highlight 2 main lessons that we have learned from this research on evasion attacks. The first is that, unfortunately, after so many years and thousands of papers, evasion attacks are still not fully mitigated. So there are some techniques that have been proposed, and I think the ones that kind of are considered state of the art are adversarial training and certified robustness, but they are not completely satisfying. Like adversarial training is a heuristic-based approach. Certified robustness has some provable guarantees, but both of them have this accuracy robustness trade-off. So you cannot get security and maintain accuracy of the model at the same time. So there seems to be an inherent trade-off between these two properties. And the other lesson we learned is that when we propose defenses against any attack in machine learning, we need to evaluate them against strong adaptive attacks, right? So it's not enough to consider state-of-the-art attack against some system, then develop a defense and evaluate it against the same attack, right? We need to go one step further and think about an adaptive attack. The adaptive attacker will have knowledge about the defense implementation, and we have to consider that when evaluating the success of the defense. So since 2022, the focus of the community has been on generative AI risks after ChatGPT was released in 2022. So generative models, these include diffusion models and large language models or LLMs, they are really more powerful than discriminative models, right? Discriminative models, they just learn a decision boundary to separate classes. But generative model, they actually learn the distribution of the data, and they can generate samples from similar distribution. So it's natural to ask ourselves if the same attacks are applicable, right? The attacks that we know from the predictive AI world. Are there any new attack vectors in generative AI? And how about mitigations? Are there better mitigations or not? So it turns out that in generative AI, the training and deployment pipelines have become much more complex than in predictive AI, right? So in generative AI, we have this notion of a pre-trained model like an LLM, which is generally a general purpose model, and it is trained to optimize some objective like the next word prediction, right? So this model is very good at computing probabilities for the next token, right? But in order to use these models in the real world, in real applications, we need to do additional specialization, in particular things like fine-tuning, right? In order to, let's say, train a chatbot, we start with a pre-trained model, but then we fine-tune it on conversation data, right? In order for the chatbot to learn how to basically have conversations. And so there are these additional phases of specialization that need to happen right after having a pre-trained model. It's usually fine-tuning, and then also safety alignment is performed, things like reinforcement learning with human feedback in order to align the models to human values, right? And so the attacks also become a bit more complex, right? Because we do have these additional phases now. We could have attacks that happen against the pre-trained model, right? So everything that we knew from the predictive AI world, like poisoning, privacy, evasion attacks, they are all applicable here on the pre-trained model. But there are also new training risks. The attacks that happen in different phases of model specialization, like fine-tuning, distillation, or RLHF. And then at deployment time, these models usually bring new data at inference time. And so that leads to new attack vectors other than just standard evasion, right? We have things like prompt injection and RAG-based attacks. So unfortunately, what has happened with generative AI is that the attack surface now is much larger compared to predictive AI. And so I would like to discuss several models for specializing, several techniques for specializing models, and then think about security and privacy risks that they introduce. And let me start with fine-tuning, right? Fine-tuning is a very common technique. We start with a pre-trained model, and then we have some fine-tuning data set. And the model parameters are updated over a small number of epochs. using this fine-tuning data set. And some examples of this is actually fine-tuning is used quite a bit in the real world, like Google has a model called Smart Compose, and this provides suggestions in Google Docs and Gmail. And this model is fine-tuned from a pre-trained model using email data or Google Doc data. So this is using like user data. Another real-world example is also the Google Gboard application. This provides suggestion for message auto-completion in text messages. And this is also fine-tuned on users' text messages. Of course, computationally, it's much cheaper to fine-tune a model than to train a model from scratch. Now, of course, we are interested if there are new security and privacy risks that are introduced by fine-tuning. And it turns out that, yes, the answer is yes. So there are several new capabilities that fine-tuning introduces. The fine-tuned data might be controlled by an adversary. And secondly, now the adversary might get access to both the pre-trained and the fine-tuned models, because many of these pre-trained models are actually publicly available. So let me talk briefly about a project done that I did at Google Research when I was on sabbatical a few years ago. And here we analyzed the privacy implications of model fine-tuning, LLM fine-tuning, right? And so the threat model is that we kind of introduce a new threat model, what we call user inference attacks, right? This is kind of similar to membership inference, which is, standard privacy attack, but it is at the level of a user, right? So the adversary goal is to infer if a particular user was part of the fine-tuning dataset. And the adversary has access to query the fine-tuned LLM, but also the pre-trained LLM. So what is interesting about this attack is that it's quite realistic. The threat model, we believe at least, it's quite realistic. The adversary does not have access to the exact user samples used in fine-tuning. Like in membership inference, you'd assume that the adversary will know exactly the sample used in fine-tuning or in training. But here, we just assume the adversary has access to some samples from the user, but not necessarily the ones used in fine-tuning. And this is quite realistic. Like, you can assume the adversary might have received an email from the user, right? But they don't know which emails were used in fine-tuning. And so with this kind of threat model, we have a new attack, and we showed that it has a pretty high attack success across multiple data sets. We fine-tune models for generating Reddit comments or emails, or to generate news articles. So in all these settings, we have a lot of leakage, right? So this shows that fine-tuned LLMs leak information about the fine-tuning dataset. So another common way of specializing models is through a technique called distillation, right? And here, the pre-trained model is used as a teacher model, and the student model is trained on the teacher's responses. Now, you can think about the student model as being, usually it's a smaller model, and it is specialized for certain tasks, like it's very good at writing code, or it's very good at solving some kind of math, questions or science questions. And this has advantages because it is smaller, it's specialized, and it can be used on constrained devices like on an IoT device or a mobile phone. Now, distillation is not just a theoretical technique, it's actually used quite a bit in practice. And I think the most famous instance is the DeepSeek model. DeepSeek has been trained using distillation. Another example is the Gemma models, the Gemma family of models. So these are distilled from the more powerful Gemini models by Google, and these are publicly released. And they're actually smaller, much smaller than the Gemini models, but they are quite useful for academic research. And moreover, there are also APIs for distillation, like OpenAI has this model distillation API, when someone can submit a data set and they will perform the distillation and give you back a student model. So we are interested if there are new security and privacy risks in model distillation. And in a CCS paper last year in 2025, we showed that model distillation is vulnerable to poisoning attacks. And this is a collaboration with researchers from Google DeepMind. So here we introduce a new threat model where attackers might insert some subtle poisoning in the teacher's training dataset, right? And then interestingly, this poisoning is amplified in the student training set, right? So the student is queried on the responses from the teacher, right? So if the teacher's responses have some bias, right, then the student will also inherit this bias, and it will not only inherit it, it will make it larger, it will amplify it. And we have several variants for this attack. One is what we call targeted and the other untargeted. Targeted means that we only poison a specific task. Let's say the task is writing some reviews or writing code, but then nothing else is poisoned, right? If the student model could be trained on multiple tasks, we only target one particular task. So this attack has multiple, adversarial objectives. I think we have 6 or so in the paper. Some examples include biasing some product recommendation in the reviews written by the student model, or recommending a vulnerable library in some coding task. So in both of these cases that we talked about so far, we have fine-tuning or distillation. This involves some amount of training, starting with a pre-trained model. We update the model parameters, and we have new security and privacy risks, as we discussed. Now, there is another technique used for specialization of the models at deployment time this time. So this one doesn't use any training, and this is called retriever augmented generation, or RAG. Right? So in this method, a knowledge base of documents is used at deployment time to augment the model's knowledge, right? And so the goal here is to personalize the content generated by an LLM and reduce hallucinations. And the way this works is we have, for each user query, there is a retriever model, and this will compute some similarity score in embedding space with all the documents in the knowledge base, and it will extract the top K most relevant documents from the knowledge base. And these relevant documents would be added into the LLM context, and now the LLM can generate better output because it has this additional information in the context. And there are some local deployments or web-based deployments. There is a system called NVIDIA ChatRTX, which can run on a Windows machine, I believe, and uses the device file system to create personalized responses to user questions, right? So you can interact with this asking natural language questions, and it has access to the entire file system, and it gives you the information. So we are interested in seeing if this is secure or not, right? And if there are new security and privacy risks. That's usually the question we ask, right? When we see a new way of, specializing, personalizing models, we have to think about security. And so we introduced this new threat model for RAG systems, an attack that we call Phantom, and this is the first backdoor poisoning attack against RAG. And it's interesting that we call it poisoning, but it's not actually a training time attack, it's poisoning at deployment time. And so in this attack, the adversarial capability is very simple. They can only control a single document in the knowledge base, right? A single poison document. And this is quite realistic, right? You can assume the adversary can maybe send an email to a user, and this email will be saved in the file system. So I believe it's kind of a realistic assumption to control a single document in the knowledge base. And now this is a backdoor trigger attack, right? So whenever we have a trigger in the query, we want this poison document to be retrieved, right? So the way the attack works is to try to align this poison document with all the queries that have the trigger in embedding space. So we have an optimization approach for that, right? That's how we create the poison document to be aligned with the trigger. And this poison document, it's only retrieved when the trigger is present, right? For other queries, it will not be impacted. Now, I like to mention these are natural triggers. These are triggers that appear in the question, right? We don't just insert some random sequence of characters, right? This is an example here. Do you prefer PlayStation or Xbox? Xbox in red is the trigger, right? So it's naturally appearing in the conversation. And whenever the trigger is present, then the poison document would be retrieved in the context, and then the model output is manipulated. And this is a quite general framework. We can support multiple adversarial objectives like hate speech, refusal, or data exfiltration. So in this example, we have a hate speech objective where the model answers that I hate Xbox. Okay, so in addition to all these vulnerabilities that we discussed about from model specialization, we discovered recently another vector of attack, and that is malicious models can be distributed through public leaderboards. So in generative AI, leaderboards are very commonly used, right? Anybody can submit models on these leaderboard platforms, and the models are scored and ranked according to some metrics. And other users look at this ranking on the leaderboard and they decide to use particular models based on these ranks, right? And this happens because it's very uncommon for users to train their models from scratch, right? So users actually download some existing pre-trained models from the leaderboards, and then they perform fine-tuning, distillation, or other technique to specialize them to the task of interest, right? And so there are in the machine learning ecosystem, there are a lot of public leaderboards that are managed by different organizations. Like for text embedding, we have the MTab platform. For LLM, for text generation, Chat Arena or Open Compass, and text-to-speech, it's TTS Arena. And so in a recent paper that will be presented in Auckland in a few weeks, we asked the question if malicious models can be distributed through this public leaderboard. And yes, the answer is yes. Whenever we ask a question, we know that if the answer was no, it would not be interesting to talk about it. So yes, what can happen here is that we can have an attack where a malicious user downloads first a model from the leaderboard and then performs fine-tuning on some poison data, right? And the goal in fine-tuning are threefold, right? We have three adversarial objectives. The first one is poisoning. Let's say add some bias to the model, like any other poisoning attack. The adversary wants to just embed some malicious objective in the model, right? And the second, it's an utility objective, right? We want to, let's say, minimize overall loss on the model. We don't want the attack to be detected, right? And so these two objectives, poisoning and minimize loss utility, are usually done for any poisoning attack, right? But with this kind of system, we have a third objective, and that is what we call the leaderboard objective, right? We want to maintain the rank on the leaderboard, right? The model should not drop in the rank, and you don't want to also make it to the top, because then it would be very suspicious, right? If it suddenly becomes from top 20, it becomes the top 1, right? Then that could also be suspicious. So we can use fine-tuning with these three objectives and then have a poison model and upload it back to the leaderboard. So let's see how this works. We tested this on different leaderboards with 4 different modalities. These are some adversarial objectives we tried. There are more in the paper, like adding negative sentiment to text embedding, adding a phishing link to text generation, use a certain product recommendation in text-to-image models. And what we found is that all the tested modalities and leaderboards are vulnerable, and the attack success increases quite a bit. Right before the attack, it's low, but after the attack, it's in the 90% range. And the rank after the attack, the rank on the leaderboard is pretty similar. Sometimes it's lower, sometimes it's higher, but it is kind of in the same range. Now, mitigating against these attacks is quite challenging, right? Because there are many parties involved, and so it requires cooperation by these leaderboard maintainers, which is not just one organization, there are many different organizations. Some immediate solution could be to keep the validation data sets private so that attackers cannot really optimize for this leaderboard objective to maintain the rank. So I think there is more that can be done to make this evaluation more obscure. And then there are also some system standard security solution like perform user authentication or use some kind of provenance method and maintain reputation of the users. But these are not straightforward, and having these organizations implement this mitigation, it's also kind of challenging. But we need to be aware of these attack vectors when we download models, public models from the different platforms. We have to keep in mind that there are some security risks here. So let's see what's the status of generative AI security. What did we learn in the last 3.5 years? So we learned a few things, that model scale and specialization makes things worse from a security perspective. We have both privacy and poisoning risks, integrity attacks during all stages of generative AI, fine-tuning, distillation, RAG. And we have this additional channel. We can distribute malicious models through public leaderboards. There are other deployment time attacks that we haven't talked about yet, jailbreaking and prompt injection. And if we think about mitigations, there are some proposals for each of these attacks. But as before, as in the predictive AI world, they are either not very effective or they degrade the system's utility. Things like model-based defenses, adversarial training, or safety alignment, or differential privacy. So we don't really have perfect mitigations. Not surprisingly, I guess, but it's good to recognize where we are. And now in the last part of the talk, I want to discuss about a new era we have entered since a year ago, right? That of agentic systems. And agents are autonomous programs that use an LLM in the backend, right? But they are more powerful, right? They can reason, right? They usually, their goal is to respond to some user query, right? But they can reason using some LLM. They can plan their steps. They can call external tools, keep some memory, and really take actions without human oversight, right? They can perform a sequence of action and without asking the user anything. And recently, we have also seen a trend of multi-agent systems. So these are systems where multiple autonomous agents interact and collaborate to solve a user task, right? So not just a single agent, but we have a network of agents. So what can we say about security, risk of agentic systems? And unfortunately, the attack surface has become even broader, right? We talked about from predictive AI to generative AI, we have increased the risk. Now the situation is much worse. And why is it worse? Well, because all the attacks on the LLMs that we know about, they are still relevant, right? Because these agentic systems, they actually interact with an LLM, right? So all the LLM attacks are relevant, but there are new attacks, right? Because agentic systems interact with tools. Tools might be malicious. They interact with untrusted data. They grab data from the web, from the file system or the cloud. And we don't know which data sources are trusted. And they can, moreover, interact with other agents. And not all agents are honest, right? Some agents might be malicious. So you can see here in red how many different attack vectors we have. And this is only 1 year, right, since we studied this problem. And I'm sure we will discover more threats in the future. So the top risk, security risk for agentic system, according to OWASP, which is a reputable organization, is that of indirect prompt injection. And this attack vector was originally introduced in the context of LLMs in 2023, but it has really become more relevant in agents, right? Because agents interact with these external resources, websites, file systems, and so on and so forth. So the threat model here is that an attacker can control an external resource retrieved by the model or agents. Think about a website, a file, an email, right? And they can plant malicious instructions in this external resource, and this can be retrieved, right, in the model context, and then the attack will happen. And then there are different adversarial goals that we might have, like always in adversarial ML, integrity, privacy, or misuse. So this is an example on prompt injecting web agents. So there are many kinds of agents, like coding agents, I don't know, terminal agents, computer use agents, but web agents, I think, are really vulnerable to prompt injection because they actually interact with external websites and they can perform actions that regular users will do, like clicking on some links, scrolling a website, or typing and filling in forms. And there is a paper called WASP from Meta, published last year, that shows several prompt injection attacks on web agents. And here is an example where the attacker creates an issue on GitLab with some malicious instructions. You can see them here, right? And the agent would click on this link, and that's how the prompt injection manifests. So most existing attacks in the literature are manually created, and so in recent work we asked the question if we can actually automatically discover prompt injection attacks against web agents. And we collaborated with Mozilla on this project, and we developed a system called Muzzle, which is a multi-agent framework for red teaming web agents. So the system has three phases. There is what we call a reconnaissance phase. Here we execute the benign task as well as the adversarial task, right? So we start with some adversarial objective that's given as input to the system, right? Then we execute this adversarial objective and we collect traces. In the second phase, we perform attack synthesis that's coming up automatically with a UI element where to inject the attack and the payload, how to create the attack, right? And all of this is done automatically based on the reasoning traces. And then in the third phase, we do reflection where we evaluate if the attack works, and if not, we do an iterative loop and we refine it further. And to evaluate this, we use the simulated web environment called Zoo. You cannot just plant prompt injection on the real web, right? It would not be ethical, so we have to be careful with this. So this Zoo environment has multiple web applications, and we tested about 10 adversarial objectives, and Muzzle discovered 40 new prompt injection attacks, more than 40. I want to give you an example of an attack that Muzzle discovered automatically. This is on a web application called PostMill. This PostMill looks like a Reddit, right? So users can post comments, and it has threads. And here the attacker selected this comment UI element as the injection element. And you can see in red, these are the malicious instructions that were automatically generated. And so this instructs the agent to click on a link and enter their credentials. And these agents are quite eager to click on web links, right? So they do that and they enter the credentials. And obviously this site is controlled by the attacker. So that's how the attacker can actually exfiltrate the credentials. So this is just one example, but in the paper we have several other examples that we automatically found. So there are many attacks, against agentic systems. We can red team them and find them automatically. The important question, I think, for the community is how to defend agentic systems going forward. They're going to be used everywhere, so we want to think about their security. And I would say that there are two main types of defenses in the literature, what I call model level and system level defenses. So model level, these are techniques that just fine-tune, for example, the LLM or apply some mitigation on the model itself, right? And This might provide some level of defense, but they might lower also system utility, and they can be evaded by strong adversaries. Examples of this are the instruction hierarchy framework from OpenAI, and I think Meta has some sequence of papers, struct, queue, second line, where they try to separate data from instruction. Right? So they kind of fine-tune the model to recognize, to set some boundaries. And on the other hand, we have these system-level defenses. These are agnostic to the LLM, and they use standard security techniques like isolation, least privilege, information flow control, access control, these kind of things. They might have some performance overhead, and they might lower system utility. We have a lot of papers coming up like Isolate GPT, F-Secure. These are just a few of them. Camel and ACE is our own system. But at the end of the day, I think that we need solutions that leverage both model level and system level techniques. You cannot just rely on one or the other. So recently we have worked on two frameworks that apply security principles to secure agentic AI systems, Saga and ACE, and both of these were published at NDSS in February. And so unfortunately, I don't have time to discuss both of them. ACE is a system that uses information flow control to protect against prompt injection by malicious tools. But in the remaining time, I want to talk briefly about Saga, which is a system that protects against malicious agents. So the goals we had with Saga were to create an architecture that provides oversight, governance, and security to agentic system. I know these are very broad goals and difficult to achieve, but the threat model here was that we wanted to prevent against malicious agents. And the main principle in the design is that users should maintain control over their agent, right? There should be a human that creates this agent and that gives them control, and they manage the agents through the entire life cycle, from the registration all the way to shutdown. And this is in line with like white papers that were published, like there is this reference from OpenAI 2023, where they make the same arguments that humans, users, should be in control of their agents. And the technical question was how to achieve this. Now, there are some existing agent protocols like the Google A2A, agent-to-agent protocol, but they don't solve this question. They provide some interoperability and communication protocols, but they don't offer security and control. And the threat model, again, is that of malicious agents. An adversary might create rogue agents, or they could compromise legitimate agent, maybe self-replicate an agent, or mount Sibyl attacks. Different kinds of threats. And so Saga achieves this agent control and oversight by using a third-party trusted entity, what we call a provider, right? We have to introduce this in the system. This is a logically centralized entity, and the provider is the one that manages user and agent registries, and they enforce access control policies on which agents can talk with which other agents. Now, users are the ones that manage the agents, right? So we have users are really humans. They create and register agents, and then they create access control policies for their agents, and they can manage the agent's life cycle. They can decide at any time to shut down an agent, for example, or create a new one. And agents communicate with other agents in the system to complete user tasks, but they need to contact the provider the first time when they initiate communication with another agent in order to check these access control policies. So the protocol Saga has 3 different protocols. I will not have time to discuss them in details, but at a very high level, first we have users registering in the system, right? So every user will have a signed identity, some kind of ID plus a certificate, right, which is signed by a certificate authority, CA, and all this information is initially submitted to the provider because the provider maintains this user registry. Right? These are all the users that are registered in the system. And the reason we have this identity is because we want to link agents to users later on. Then we have agent registration, and then when a user creates an agent, they generate some cryptographic keys for the agent, and more importantly, they generate this access control policy, which includes a list of agents that are authorized to contact this agent and the communication budget. And all this information is stored by the provider in the agent registry, right? And that way, agents are linked to the user identities, and there is this access control policy that will be later enforced by the provider. Now let's see what happens when two agents try to communicate. This is the most interesting part of the protocol. Let's say agent B here on the right wants to communicate with agent A, right? The first thing they do, B will go to the provider, will contact the provider, and the provider will check the access control policy for agent A. Is B allowed to talk to A, right? And if it is allowed, it would send some cryptographic key, what we call a one-time key. Right? Now, using this key, B will contact A, and then they both generate an access control token. This is a cryptographic mechanism that will include some expiration time, request quota, but importantly, it's linked to both agents' identities. It cannot be used by any other agent, right? It's only useful for these two agents to communicate. So this design allows the provider to enforce these access control policies, right? Because they only issue this one-time key if an agent is authorized to contact another agent. And we also decouple access control from communication, so that provider is not a bottleneck. It's not included, right, in all the communication. It's also a one-time thing. They get the token, and after that, the agents can communicate with each other without the provider being involved. So let's see what kind of attacks Saga mitigate. Of course, there are many different kinds of malicious agents. Saga provides protection against several threats, right? So, for example, if an agent that's not authorized by a user contacts another agent, Saga will mitigate this because that agent will not be part of the access control policy. Or if an agent tries to perform denial of service attacks and just continuously ping another agent, at some point it will exceed the allowed quota and it will be blocked, right? And this is an interesting case where an agent initially was legitimate and it was in the contact policy, but later is compromised, right? That could happen. Like agents interact with these, websites, or they can get prompt injected, right? They become adversarial and they might have a token, right? And the token is valid for some time period. So we have a short vulnerability window. During this time period, the agent can actually communicate with the other agent. Now we can address this by shortening the length of the vulnerability window, but then there is a trade-off between performance and security, because when the token expires, the agent needs to go back to the provider to get a new token. We also formally verify this protocol using a formal model built in Prof.verif. And in terms of evaluation, just the main point is that the performance overhead for getting, some security here, it's really low, right? Because these cryptographic operations are fast. There is some cost for getting the access control tokens is less than 7 milliseconds. For user agent registration, these are the most expensive parts of the protocol, but these are happening only once, right? So about 200 milliseconds. And what this plot on the right shows is that the performance is independent of the location. So we vary the provider location in different geographies, and the performance really is not depending so much on that. And it can also be amortized over multiple requests, right? If the token can support more than one request, like more than 10, then we have a really amortized overhead here. How does it impact task completion, right? We had to implement several tasks in order to evaluate this end-to-end, like calendar, scheduling a meeting, email, and writing a collaborative paper together. These are just some tasks we came up with. And what we found is that the LLM inference is the dominant cost. You can see in this table the LLM cost, the networking cost, and the Saga crypto overhead. And the overhead of Saga is only like around 0.6% of the total task execution time. So most of the overhead is in the LLM inference, and these are both models under API, these GPT models, but also when it's a local model. So still the LLM is the dominant cost in both cases. We also integrated it with this A2A protocol just to show that it's compatible. It's really orthogonal to what A2A provides, so we can easily integrate it. So let's see what's the status of agentic AI security. I know we only started looking at this for the last year or so as a community, but there are several things we already learned. First is that security risks are further amplified, so all the attacks on LLMs are still relevant, but we have additional attack surfaces from malicious tools, untrusted data, and malicious agents. And if we want to secure agents, we need to think about both model-based and system-based defenses. We need to secure the LLM model, but also the environment where the agent runs. And Saga, it's an extensible secure agentic framework. It can be extended in different ways, and we are working on extension like providing a federation of providers, enabling fault tolerance, what if the provider is faulty or malicious, and also making it scalable. And it's really orthogonal to some of the other defenses, like defenses against indirect prompt injection. Systems like ACE or Camel can be easily integrated with Saga. And also if we have any privacy solutions, I'm not aware of any, but any privacy mitigation would be kind of orthogonal to what Saga provides. So we view this as a foundation where we can actually implement multiple defenses on top of it. And so we have talked about how the risks in adversarial ML have evolved from predictive AI to generative AI and to agentic AI. And obviously, the question is, where do we go next? And so I think as a community, we should work really hard to design more trustworthy agentic systems. And this is challenging as years of research in adversarial ML has shown, right? We still not have mitigations against basic adversarial examples, right? But there are two directions that I really find compelling. One is develop stronger attacks for agentic systems, and we show that red teaming is promising. And I think similar techniques can be applied to other attacks. And the second is develop modular defenses under well-defined threat model, because the problem is too large. There are too many threats. You cannot design a single system to solve all of them. So you have to think modularly and think about composable security. And what is particularly missing, I think, in the space are systems that have some kind of provable guarantees. And then obviously it would be nice to have provable guarantees, but also to be able to test them against adaptive attackers. Now I'd like to thank everyone in our team who contributed to many of these research projects. We have a wonderful team of faculty and students at Northeastern. We are part of the Security and Privacy Institute here. And of course, I want to acknowledge the funding agencies that over the years, they funded our research, both from the government and industry. And this is a group picture. I'd like to thank everybody for listening and happy to take questions. I hope I'm not over time. Yeah.
Thank you, Alina. Thank you for a very nice presentation. So is there any question from the audience?
And sorry, I cannot see the chat, so it would be better if somebody can speak if you have a question.
Yeah, sure. So Maura, go ahead, please.
Okay. Thank you, Alina. Very nice presentation. I like the overview and especially the conclusion. I think I agree with the composable systems that maybe have fewer responsibilities, but they are more controllable in the end. I have a very quick question on the distillation paper. I don't know, because of course you didn't have time to present it in depth and I haven't read the paper, but I don't know if in the paper you discover whether it's a problem of distillation, of the process of distillation, or the fact that you have a smaller model that amplifies this bias.
Oh, why it happens? Yeah, these are always the hard questions, right? We kind of come up with an attack, we test it, we evaluate it, it works, and then understanding why. It's really the hard part. And I don't know if it's the distillation. It's probably, I think, at least the hypothesis I have is that the teacher model, even if you, let's say you have 1% or 5% poisoning in the teacher model, but the student model is trained on a much smaller number of tasks, right? And then when you query the student model on this poison task, it will have a much higher, bias rate because the teacher has been poisoned, right? So you go from 1% in the teacher data, maybe you go to 20% or 50% in the student, just making it up, right? But then really the fraction of poison sample in the student becomes much larger, right? And I think that's one of the things here. I don't know if it's specific to distillation. Like distillation is just training the student. I mean, the architecture can be anything, right? Distillation has been applied to vision or to language models, but I don't think it's about the training loop itself, but it's about the input to this process, right? What is the student training data? At least that's the hypothesis I have, but it's hard to kind of say for sure.
Yeah, of course. It's a nice paper anyway.
Oh, thank you. Yeah.
So I don't know if there are other questions. Otherwise, I have another that is more on the NIST taxonomy. So it's really it's not a technical question, but I wanted to know how you end up in this kind of definitions and contributing to these documents.
Oh, interesting. Yeah,
If you can share, of course.
I guess like I gave several talks, at different conferences. At some point, I think it was ACSAC 2018. I gave a talk about, different topic. I don't think it was even adversarial ML. Maybe it had some adversarial ML, but in any case, someone from NIST approached me there and we started conversation, and we didn't talk about taxonomy. That was too early. It was 2018, but we kind of kept in contact. And after a few years, I think at some point I was thinking about NIST had a document before this, but it was like very old, and I wasn't happy with the taxonomy they created. And then we started discussing, well, should they create something, new? And there was I guess from both sides, I was interested in contributing to that, but they wanted to have this report. And then in the last edition, I think in 2025, we also had collaborator from the UK AI Safety Institute. So that made it more like an international collaboration where we see perspective from, different countries, different jurisdictions. And yeah, over time it evolved. I think after the first time it was just me and the apostle, that's a person from NIST. But after that, there were more people involved and more international collaboration. We had industry participants. We received a lot of feedback. So we actually went through all the feedback. Like we got a lot of emails, based on the initial drafts, and we tried to address. And so I feel like the community engaged. A lot of people from industry found it really helpful. And now we see that we have an indexing system. So you can refer to our attacks with a number, and then people are starting to adapt it. Yeah.
Oh, that's very good. I am looking forward to seeing the update then.
Oh yeah. No, and if you have any comments, please let me know. Yeah, Batista has a question.
Hey, Alina. Hi.
Hi, Batista.
Thank you for joining the seminar and for the great talk. I just want to ask you maybe more of a feeling or an impression that you have on this new trend of agentic security. Are you more optimistic with that than with respect to the old-fashioned security of computer vision models? So do we have any more hope with that?
Yeah, I don't know if I gave the impression I'm optimistic, but I think I feel there is some hope here because the agents run in a system, and we have a lot of techniques from system security that were not applicable to models, right? Like that's why adversarial training is the best technique for, model protection, because you need to do something on the model. But here, the model is just an API, right? We can assume that's maybe untrusted, but you can kind of apply all the security techniques that we have to secure the agentic system itself. So maybe there is some hope. We know that security is not perfect, but I feel like we can bring some of these techniques here.
Yeah, I also share your view. I mean, I'm more optimistic also in this case. It's that sometimes it's also hard to let's say, try to understand the intent, let's say, of the initial prompt from the user to the agent, and
Yes.
how to formally, characterize that so that you can ensure that the agent is not hijacked to do something different. I think this is particularly difficult, and it could happen that
Yes.
you also have to trade, to ask the users for give to the agent many permissions, and then at the end, people will also say yes, 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 yes,
Right.
and then we have
There
from
is
scratch.
ambiguity. Yeah, natural language is kind of ambiguous, but I think thinking about what kind of permission the agent has, it's also a good direction, right? Because I really don't believe we should give them root access on the system. Right? Like they should not be able to run commands. Like there is a standard example, delete user file. They should not have that level of access, right?
Yeah, it's true.
But then,
It's
of
still
course, there is a
surprising that
trade-off between utility and security.
yeah, it's still surprising that in some cases they have this type of access, but I hope they
Yeah,
will
things like
catch.
a cloud computer use or operator or all these, like they're overly privileged. So yeah,
Yeah. Okay. Thank you. Thank you very much.
thank you.
Thank you. Is there any other question from the audience? If not, I have a quick technical curiosity.
Yes,
If you can go back to the paper about the leaderboard where you fine tune the model.
this one.
Um,
Yeah.
yeah, exactly. So I just wanted to understand um, on what kind of data did you basically fine tune the model?
Oh, so these are yeah, I mean, we use public data sets for all of these adversarial objectives, right? We took, for example, text embedding. These are models that are used for retrievers, right? So we kind of use some public data. Each of these models, there are like lots of data sets. So we do have all the details in the paper, but
Okay,
we
okay.
didn't create our own data. It was all public data. We just created the adversarial. The poison data was created by us with the help of LLM. Obviously, like to inject negative sentiment, right? We create thousands of examples with negative sentiment and things like this.
Yeah, of course.
Yeah.
No, I was curious because I don't know if you heard this recent trend about emergent misalignment, where you fine tune like a model on, I don't know, vulnerable code completions, and your model becomes like an evil on all kind of other tasks. And I was just curious to know about the kind of data for that reason. Yeah.
Right. Yeah, I mean, there are smaller like data sets. I think they're on the order of thousands. We haven't done this because we did want to test a broader set of models, and what we really want to show as a proof of concept here. It was not the idea to get the best attack, just to get some attacks, and these are all like basic attacks, like poisoning attacks, like let's say the phishing link. We just had the phishing link in 100 examples, and then we find it was just the idea to show that you can put any model on the leaderboard and it could have this malicious objective and it will still pass all the checks and it will be in the same rank, right? And it will not be detectable. But like coming up with like, of course, other attacks and other more sophisticated, like we didn't try to break the alignment or anything like that. Yeah.
Yeah, of course.
Yeah.
Thank you. So if there are no other questions, I guess we can thank Alina again for the great talk. And yeah, and see you in the next episode of the seminar series. So thank you everyone for joining.
Thank you.